Show by the principle of mathematical induction that for all n belonging to the set of natural numbers, the following is true. Okay, let us begin. So here we are going to first consider a statement Pn. So let P of n be the statement which is given by P of n such that the sum of the first n natural numbers 1 plus 2 plus 3 all the way up to the nth term n, and the sum is given by n times n plus 1 divided by 2. Okay, so we're going to name this number 1. So here we have a statement which is the sum of n natural numbers, the first n natural numbers, and it's given by n times n plus 1 over 2. Now our goal is to not prove this why this is the case, that why do we get n times n plus 1 over 2, but to show that this statement is going to be true for any natural numbers that we pick up. So to show that this is true, first we are going to consider n value equals to 1. So for n equals to 1, what we get is P of 1. Now P of 1 means we are only considering the first term. So we have 1. This is going to be equals to, now in place of the formula n times n plus 1 over 2, we're going to replace n value with 1. So we have 1 times 1 plus 1 divided by 2. That means 1 will be equals to 1, which simply tells us that P of n, this particular statement is true if we choose n value equals to 1. That means true for the first natural number. Now the question arises, how do we show that it is true for all natural numbers? So what we'll do, we're going to consider let P of m be a true. This is another statement we are considering that it's a true statement. That means m is going to be one of the terms of the n natural numbers, right? Now we can think of it like this. So here we have 1 plus 2 plus 3 going all the way up to, so let's say one of the term, that's m, and going all the way up to n. So this is one of the term that we are considering, and we're saying that the given statement is true for this particular natural number. And if it is true for this particular statement, then this simply tells us that P of m, then the new statement is now going to become 1 plus 2 plus 3 going all the way up to m. So m is going to be equals to m times m plus 1 whole divided by 2. Fine. So let this be statement number 2. Now, using this statement, our goal will be to show that the next consecutive natural number, makes the statement true. That means we want to show that P of m plus 1 is true as well. Now how do we show that P of m plus 1 is true? Replace m with m plus 1 such that we get P of m plus 1 such that we have 1 plus 2 plus 3 going all the way up to m, and then we also have the extra term which is m plus 1, and we have to show that this is equals to m plus 1 multiplied to m plus 1 plus 1, which makes it m plus 2 divided by 2. So this is what we want to show. Now how do we show that this is true? We will start from the left hand side. Now the left hand side of the expression is 1 plus 2 plus 3 going all the way up to m plus 1. However, in statement number 1, we have already showed that the sum of the first m terms, that's m times m plus 1 over 2, which means that we can take the first term all the way up to the second last term and replace it with m times m plus 1 whole divided by 2 plus the last term, which is m plus 1. Now we're going to combine these two terms. So combining, so let's take m plus 1 as the common factor. So we have m plus 1 as the common factor. We can also take 1 over 2 as the common factor, which means that in the first term we'll be left with m, and in the second term we'll be left with 2. Fine. Now that's exactly the expression on the right hand side. So therefore we have successfully showed that, we can say here, since left hand side equals the right hand side, this means that the statement P of m plus 1, so this is a true statement. So this is a true statement. Since this is a true statement, therefore we can finally say that hence P of n is true for all values of n belonging to the set of natural number. That means any natural number that we pick, the statement is always going to be true. So we have successfully proved our problem using the principle of mathematical induction.